Welcome to this video talking about extreme values of functions, where this one is on concavity and points of inflection. First of all, recall that a function is concave up if it's shaped like a cup, and a function is concave down if it's shaped like a round. A more mathematical way to say this is as follows. Concave up, when a function is concave up, any 2 points in the concave up region will be connected by a line that lies above the function. Okay? Concave down, when a function is concave down, any 2 points in the concave down region will be connected in a line that lies below the function. So that's the mathematical way to say it. The graph of a differentiable function y equals f of x is concave up on an open interval if f prime is increasing, and concave down on an open interval if f prime is decreasing on this. So another way to say this is if f double prime is greater than 0 or positive, which means that f prime of x, our derivative, is increasing. So if your slopes are increasing, that's what curves it and makes it concave up. Here, if f double prime is 0, that means my f less than 0, that means my f prime is decreasing. That's why it curves the function and makes it look like concave down. So any point on which the graph of a function changes concavity is called a point of inflection. So we've been talking about critical points, but now we learned this one. Here is how we can find the regions of concavity and inflection points. First, to find the concavity, you're going to take the second derivative. So we're going to do f double prime of x. Set f double prime of x equal to 0, so this is important. This is how we did critical points with f prime of x, and solve for x. Also, if necessary, find where f double prime of x is undefined. Then we're going to create a sign chart, or an f double prime bar, if you will. Where f double prime changes sign, we have a change in concavity. All right? So let's look at this. A point, here's a definition, a point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. So I'm going to draw this graph here and to show you. Here we've been looking at critical points. So we're looking here where the slope is 0. Right here would be a critical point, and right here, because the slope is 0, if this is my function f of x, excuse me, not f prime, but f of x. All right, this is our function f of x. Now, if I want to know the point of inflection on f of x, do you see how it's concave down to about here, and then it switches concavity, now it's concave up? Well, this point right here is what our point of inflection would be, is that point there, the point where it changes from concave, in this case concave down to concave up. So it's basically changes in concavity. Okay, I'm going to show you the second derivative test. It works, it's very interesting, but I usually stick with the first derivative test, and I use that all the time. But basically, if you have y equals f of x, and it's twice differentiable on the interval I, if f double prime of 0 is greater than 0, then it's concave up. If f double prime is less than 0, then it's concave down. Okay? And the second derivative test for local extrema. Suppose f double prime is continuous on an open interval that contains x equals c. If f prime of x equals 0, this is a first derivative, and if our second derivative is negative, so if our first derivative you put it equal to 0 and the second derivative is negative, then that is a local max. Okay? And if you think about it, here is like your max or min, and then since everything is below it, then this turns to be a local max because this is concave down. All right? So here's what it would look like, kind of. So that's why it's a local max. If we had our first derivative equal to 0 and we found it, and f double prime was greater than 0 or positive, then it has a local min because that means that everything of the function is above it. So it would look like that. If f prime of c is equal to 0 and f double prime of c is equal to 0, the test fails. The function f may have a local max or a local min or neither. Okay? So let's look at again our shapes of functions, and I know you've had this before, but it's nice to look at it. So if f prime of x is less than 0, means your original function is decreasing, and if your derivative, second derivative, is less than 0, then it's concave down. So I show a picture here. Here, if my original function is decreasing again, but my second derivative is greater, it's concave up. Here, my first derivative is greater than 0, so that means my original function is increasing, and it's less than 0, the second derivative, so it's concave down. Here, my original function is increasing again, and my second derivative is also greater than 0, so then it's increasing and concave up. Okay, so this is what the functions would look like. I just wanted to show you some pictures of how they would look for your notes. All right, let's do an example where we're going to find critical points in the y-intercept and everything we can find. I know everything's labeled on this graph, but it's okay. We're going to just do everything that matches it. So I'm going to use an easy function, y equals x to the fourth minus 4x cubed plus 10. So I'm going to do the first derivative to find the critical points. So that's going to be 4x cubed minus 12x squared equals 0. Then I'm going to pull out the 4x, factor out the 4x squared. So I have x minus 3 here equals 0. Make a big T, so 4x squared is going to equal 0. X minus 3 equals 0. X is going to equal 0 here, and x is going to equal 3. And you can plug these back into your original, but we can actually look at the graph. I have the point 0, 10 here, and I have the point 3, negative 17. All right, so what we're going to do here is kind of set up everything. I'll do the derivatives here, and we'll write down what we want. So we want to have, first of all, our critical points. All right. We're going to also figure out the y-intercept. We're going to do our inflection points. And if there's any vertical asymptote or horizontal asymptote, we'll put that there. In this case, there is none because it's not a rational function, but we're going to be looking at all things to do with the graph. Okay, so we're going to fill these in as we go along. So I found a critical point at 0, 10, and at 3, negative 17, and then what we're going to do is see if we can figure out if it's a local min or a local max. So we're going to do our f prime bar. And if I look at it here, I have it at 0 and at 3. And I go through this, and I'm going to come to the, remember we've always done this, go to your factored part here. And we're going to plug in some points to the left of 0 and 3. So the left of 0, I'll use a negative number, so this will turn positive, that will be negative, so this is negative. If I would use between 0 and 3, I'll pick a 1. This would be negative, this was positive, so this is still negative. And then if it's greater than 3, if I put a 4 in there, it's going to turn positive. So the only max or min that we have in this case, we have a local min right here at 317. I just did the first derivative test. So here at 3, negative 17, we're going to call this a local min. 0, 10 is a critical point, but it's not a min or a max. Okay? Now the next thing we're going to do is, this is new, we're going to find the inflection points, or the change in concavity. So I'm going to do f double prime of x is going to equal this first derivative, second derivative. And we're going to put it equal to 0. And I'm going to factor out a 12x here, so I have x minus 2 equals 0. 12x equals 0. X equals 0. The next one is going to be x minus 2 equals 0, x equals 2. So this is the point 0, 10 again, and if I put the 2 in there in my original function, I'll get 2, negative 6. So inflection points that we have here are changes in concavity. So at 0, 10, I have an inflection point, and 2, negative 6. Now it doesn't always happen this way, but every once in a while you're going to get where an inflection point is also a critical point because it's changing concavity, and it's a critical point because, but it's not a max or min, it's neither because the slope is 0 there. The other thing is we always like to do is the y-intercept. In this case, the y-intercept is also the point 0, 10 because it is crossing the y-axis at that time. Okay, so there is an example of how I want you to do one whole graph.